afternoon, and thanks for joining us. I'm Judy Simpson. In the 1970s and 80s, when the effects of acid rain were being discovered, it was a topic that was in the news a lot. You don't hear about it as much anymore, but scientists and researchers are still studying the long-term effects. Scientists at the University of Vermont recently discovered that one species is having some unexpected results years after it was almost wiped out by acid rain. Rebecca Gollin tells us more.
The toll road in Stowe might seem like an unlikely place to find a news story, but there is one here, and it's good news.
What I found during that project was that, yes, they've recovered, but the trees actually were growing better than they had in the entire record of their growth. Even a tree this size can be, 40, 50 years old sometimes.
Alexandra Kasiba is a staff scientist with the University of Vermont's Forest Ecosystem Monitoring Cooperative. She's talking about red spruce trees and a study she completed that produced some unexpected results.
So this was really surprising. We expected them to, recover, but maybe just kind of go back to status quo. And here they were growing great, growing amazing. And so this opened up, this is how science and research happens. You stumble upon stuff a little bit unexpectedly.
To understand Kasiba's surprise, we have to take a step back and look at why red spruce was an important species in Vermont.
It was so valued that when Americans cleared the land in the 1800s to have hill farms and have sheep, it was the dominant tree that they were cutting out, building with, but also exporting. Burlington, as a timber mecca, exported a lot of its red spruce up and down the Lake Champlain through the Richelieu, etc. So it was a species that kind of loved to death.
Paul Schaberg is a forest health and productivity specialist with the U.S. Forest Service. He comes in to investigate when there are unexplained or unexpected changes in tree health.
Tree species suddenly starts to decline, the crowns are dying or its growth is going down, and we can't figure out why. It's not insects on the tree or something. Then we start doing studies to try to evaluate what's going on, why, and, can we correct that?
Schaberg has been studying red spruce trees here in Vermont for decades.
Red spruce, from a human standpoint, is an amazing tree. It has a straight stem. It grows very well normally. It has very strong, lightweight wood. It's great for construction, but it's also really great for making musical instruments.
In the 1970s, researchers noticed that the red spruce that remained, mainly at higher elevations on mountains and hillsides, were dying. But that wasn't the only thing going on then.
That decline coincided with when we first realized that the precipitation coming down, rain, snow, and fog water, was very acid. This had been discovered in Europe, where industrialization happened much earlier and pollution standards were pretty much non-existent. But it was only with someone in New Hampshire at the Hubbard Brook Experimental Forest studying the water cycle, saying, "Oh, let's measure the pH of this," that they were, shocked. It was, hundreds of times more acidic than what they thought it should.
It was a puzzle for scientists at the time. They knew that the precipitation was highly acidic and that the red spruce, a formerly dominant tree in the area, was declining for no apparent reason. That's when they began to wonder if there was a link between the two.
Folks like Hub Vogelman at UVM started saying, I wonder if these are connected. And that began actually a tremendous scientific effort.
UVM professor of botany, Hub Vogelman, was crucial to the discoveries that came next.
To begin with, Hub, just how serious do you think the acid rain problem is?
Well, we think it's quite serious, and probably more serious than a lot of people believe today. Here's a picture I took a couple of years ago. It's at an elevation of about 3,000 feet on Camel's Hump. It's facing west toward the Champlain Valley. you can see a large number of dead trees, including well, mostly they're dead spruces.
The work of Vogelman and others led to the 1990 amendments to the Clean Air Act, which reduced the sulfur and nitrogen that were the main culprits in making the precipitation so acidic. But Schaberg was not done with red spruce just yet.
We kept looking at red spruce. So we actually, in the 1990s and early 2000s, figured out what was the mechanism. What was it about acid deposition that was reducing the cold tolerance of red spruce and making it susceptible to freezing injury?
It was the last piece of the puzzle about why the red spruce was so affected by acid rain. The key was calcium, which the acid deposition leaches out of the soil, leaving the tree more vulnerable to the cold. A massive winter injury event in 2003 further damaged Vermont's red spruce population. It was a few years later that Kasiba began the work that led to her study.
We were still looking at what we thought would be the downward trajectory of these trees that had been so badly damaged in 2003. And indeed, she found that the trees were growing much worse for 3 and even 4 or more years after that winter injury event. But she studied that far enough away from that big event that even though there was this decline for years, then the trees rebounded and they started growing better and better, so that they were growing the best they ever had in their entire lives. And that was shocking.
I was looking at that. Why is this happening? What are the climate, environmental reasons that could explain this growth? Is just happening in some plots? Is it because of our complex land use history? There's so many different factors that affect growth. And so taking a large number of samples, so looking at a lot of trees, over 700 trees, a large range of sites, so we're not just looking at one state or one location, so it kind of tears out all that variability, and then doing a lot of statistical processing, we can actually look at what climate or environmental variables explain that growth increase.
Working with collaborators from around New England and New York, Kasiba looked at samples from over 50 sites. She found that lower amounts of acid precipitation were pivotal to the renewed growth, along with the unique ability of red spruce to use the weather to its advantage.
It has this ability to photosynthesize in the winter when it's somewhat warm, when we have those January thaws, or it can take advantage of if we have a really mild fall and all the sugar maples and the red oaks have lost their leaves. Suddenly these conifers are just sitting there. Red spruce has this ability to then take advantage.
Well, this is certainly good news for the red spruce. The work of these researchers is not done.
We now have a remarkably good understanding of the trajectory and the niche of red spruce, a very important species, but red spruce grows in a forest with lots of other species. And one obvious question that comes up is, so red spruce is doing all right, what about these other trees?
It's a great story for right now, and we don't know what the future will hold for red spruce and for other trees in our forest, and that's why we continue to research these things and look at growth, look at physiology, look at how climate and environmental factors are affecting these trees, because we need to understand those dynamics to predict future changes and what will happen.
It's a good news story for now, but the ending still isn't written. And that's why these researchers don't plan to stop until all of their questions are answered. In Stowe, I'm Rebecca Gollin with Across the Fence.
Thank you, Rebecca. Joining me now is Alexandra Kasiba and Paul Schaberg, who we met in the video. Alexandra is a scientist with the University of Vermont's Forest Ecosystem Monitoring Cooperative, and Paul is a forest health and productivity specialist with the U.S. Forest Service. Thanks again for coming in.
Thank you.
Now, Alexandra, for your study, you looked at samples from over 700 different trees, individual trees, I should say. That sounds pretty labor-intensive. How did you get those samples, and then what did you do with them once you got them back to the lab?
It is very labor-intensive. We actually
take a little increment borer and core the tree and extract a pencil-sized piece of the wood. And so we relied on collaborators in the region to get a larger scale, spatial scale of data. And scientists are doing this more and more, looking at broader scale questions. And so it needs a lot of people to do that work. And I brought actually in a tree core, which is an example of what we extract. But that's the first step. And then from there, we actually have to correctly date each individual ring. So we have to make sure that if we say it's from 2010, it actually is. That can be quite a lot of work to get that point.
And so what did you find out from these samples?
We can find out a lot of things. We looked at the response of environment and climate, as well as some site characteristics on the growth. But scientists, climatologists have used tree cores to reconstruct historical climate. You can look at productivity for timber, so how much carbon sequestration are trees doing every year, carbon storage, response to insects and disease. There's many questions. And the beauty of a tree core is that with one sample, this is 170 rings, so a 170-year-old tree about, and you get a year of data for each one of those years.
That's incredible. So this information is being used for a lot of different things.
It is, and that's actually why we've created a dendrochronology database, and so it's a repository for scientists to put this data available to other researchers so we can ask really broad-scale questions using lots of trees across many species.
Now, Paul, as you said in the video, there are a lot of other kinds of trees in the forest besides the red spruce, some of which are also vulnerable or sensitive to damage, like the sugar maples. Any sign of a rebound in these other species?
Well, not yet. So we've been looking at that and just starting to do a similar broad-scale analysis. We suspect that there should be, but there's also reasons why sugar maple may be slower to improve because there's a lot of other stresses other than winter temperatures that restrain its growth.
And so what other effects did the acid rain have on the forest ecosystem?
Acid rain had many effects, and tree health was actually one of the later ones we looked at. Acid rain mobilized heavy metals and things like aluminum and put them into lakes and rivers. There was very famous fish diebacks in the dead lakes of the Adirondacks.
Right.
It even eroded monuments like statues and things, and even infrastructure like bridges. So it had a lot of effects.
And so are these areas recovering?
So some of those areas we definitely know are recovering. The lakes are improving. There's less erosion of infrastructure, but we haven't looked at everything. Soils are starting to recover, but not entirely.
Makes you wonder what it was doing to us.
Well, actually, there were studies to show that if people were hiking and breathing in air from clouds that were acidic, that it was damaging to lungs.
And so, Alexander, are you seeing this success everywhere that red spruce grows?
We are, and in fact, there's some researchers that are looking at red spruce growth in the mid-Atlantic and southern states, where red spruce is much more constricted to high elevations due to logging and severe acid rain, and they're also seeing a rebound. And what's interesting, even in places in our region like Maine, where there wasn't quite as much acid rain, we're seeing increase in growth too. So it seems quite broad scale.
And so, Paul, how did you and your team make the discovery about calcium deficiencies that are making the trees vulnerable?
Well, at first we did it by studies in the laboratory, very controlled studies. But then as we learned more, we moved out to the landscape. And one of our more important studies was looking at tree health on an entire side of a mountain that at Hubbard Brook Experimental Forest, where they added calcium back to a whole side of a mountain and looked at the effects. And those results were quite important to us, saying, yeah, this is a forest-wide response.
That's incredible. And so how long did it take the trees to recover once they got the calcium back?
It's taken a while. So the soils were so depleted, and the calcium is very slow to build back up. It has to come from the mineral weathering of the bedrock material. So it's a very slow process.
I would imagine there'd be kind of an expensive process if you were trying to add it back to the soils too.
Yeah, so they've actually done some of that in Europe, where there was a greater concern, and it was very visible, but it's not something we do in general in the States.
But overall, this sounds like it's a pretty good news story.
Oh, definitely. I think it's a very good news story.
Well, I want to thank you both for joining me today. And that's our program for today. Thanks for joining us. I'm Judy Simpson. I'll see you again next time on Across the Fence.